Hello, Kagglers! I'm gonna do my traditional chillin' for a sec while I wait for the stream to start, make sure that everything is working well. Alright, looks like it is. Hello, and welcome to the Kaggle Reading Group. Last week we kicked off with EfficientNet, and this week we're gonna continue to read that paper. We might finish it today. I think we'll see. And the link is in the video description down below to the paper. And if you cannot see it, you can try searching EfficientNet, Rethinking Model Scaling for Convolutional Neural Networks. There we go. So you can see a little bit better. So, just a little refresher about what we have read so far. You may be familiar with convolutional neural networks, very commonly used in computer vision, especially. And we know from sort of like the last little bit in machine learning that in general, a bigger model, more data, training for longer does better on some problems, on most problems. And the question that this paper really tackles is, how can we best make a bigger model? So it's really common to train a small model and then increase the size along one of three parameters. So, sorry, itchy nose. So the parameters that people generally will increase the size along are width. So for convolutional neural networks, those are channels. Depth, so adding additional layers, and then resolution, so using pictures with higher resolution, because this is, again, usually images. And what this paper proposes is a method to increase all three of those dimensions at the same time using learned parameters in a way that will work particularly well for the problem at hand, whatever that problem is. And hello, good morning for people who are joining the stream. Well, morning for me. I think it is quite late at night in India. So the first proposal is the first thing that this paper does is it proposes this way to scale the models using learned parameters. And the second thing that it proposes is a class of models found using automated machine learning, so neural architecture search, that seem to work particularly well and scale particularly well. And we have not read that part of the paper. So compound model scaling, we talked about this. The 3 dimensions, the depth, so number of layers, the width, the number of channels, or the size of the network for, text applications, model width might be like the size of the sentence that you're looking at, or the text span, instead of the number of channels. And then resolution is the size of the image going in. So the place where we left off is this observation, which is based on a bunch of related work and just sort of the state of the field, that if you make your network wider or deeper, or you make your images bigger, they all improve accuracy, but they also all start to decay. So you can see that you get a lot of improvements in the first set of, so as you increase the number of floating operations per second, long operations per second, I guess. No, I think it's just floating FL. The number of floating operations per second, near the beginning, you get a really large jump in accuracy, and later on, that improvement rate decays. So you don't continue to get sort of linear improvement as the model starts getting bigger. All right, so what if you scale multiple things at the same time? Let's pick up here. So section 3.3, compound scaling. Let's zoom in a little bit. We empirically observe that for different scaling dimensions, are not independent. Intuitively, for higher resolution images, we should increase network depth such that the larger receptive fields can help capture smaller features that include more pixels in bigger images. What? Okay, so as the images get bigger, we need to have a deeper network because deeper networks are able to describe a more complex decision space, and we want to be able to capture similar features that may be spread across more of the image because the image itself is larger. Correspondingly, we should also increase network depth when resolution is higher. Isn't that the same thing? I guess correspondingly. In order to capture more fine-grained patterns with more pixels and higher resolution images. These intuitions suggest that we need to coordinate and balance different scaling dimensions rather than convolutional single-dimension scaling. So as your images get bigger, you need more model in order to handle them, so you should scale them together. To validate our intuitions, we compare width scaling under different network depths and resolutions as shown in Figure 4. If we only schedule network width W without changing depth D equals 1 and resolution R equals 1, the accuracy saturates quickly. So you get to that point where additional depth increases don't help you, or width increases don't help you. With deeper and higher resolution width, scaling achieves much better accuracy under the same flops cost. So you don't need to do more operations, so it's faster to do inference, but you get better results out. These results lead us to a second observation. Observation 2. In order to pursue better accuracy and efficiency, it is critical to balance all dimensions of network width, depth, and resolution during ConvNet scaling. So we have sort of 3 knobs that we can tweak, and if we tweak them all at the same time, then we get a larger, better model, basically. Or a smaller model that's better at the problem. Mismo says, how much time does it take you to read and understand the whole concept behind any paper? Well, I'm doing it live. So usually between 2 to 4 hours per paper. Roughly. Ravinder says you have a cold. I think it's allergies. I didn't take my antihistamines this morning. All right. In fact, a few prior works, Zoff et al. 2018, Rial et al., or maybe Rial et al. 2019, have already tried to arbitrarily balance network width and depth, but they all require tedious manual tuning. So increasing the width and the depth together gets you a better result, but the previous work, you have to do that hyperparameter tuning by hand, and they're proposing an automated way to do it. And let's actually go up and look at this figure really quick. So scaling network width for different baseline networks. So we have here we are increasing the width, and we have a still very shallow and low resolution network. This is the blue, and the green is deeper but still low resolution, and then this sort of like yellow-brown color, I don't know what that is less deep but has better resolution, and then this top red line has is a deeper model and also has higher resolution. So as you can see, if we're looking at 5 billion flops, the model which is wider and deeper and has higher resolution is performing better with fewer operations. And this wasn't necessarily, like, this is something they had to validate. This, you can't just like be like, here's my intuition. I'm never going to check it. I'm pretty sure it's right. That's not good science. All right, in this paper, we propose a new method, compound scaling method, which uses a compound coefficient, phi, I think that's phi, to uniformly scale network width, depth, and resolution in a principled way. So depths will be alpha phi, widths will be beta phi, and then resolution will be gamma phi. And then ST. I don't know what ST here means. If anyone does, please pop in the chat. Will be alpha times beta to the second times gamma to the second, and that will be proportional to 2. So I think what they're saying is that we want width and resolution to increase faster than depth, I believe is what this is saying. And then alpha is greater than 1, beta is greater than 1, gamma is greater than 1. So we don't want to make any of these dimensions smaller. We want to make sure we're always increasing all of them. All right. How many papers have you written up to now? Oh, maybe like a dozen, maybe? I haven't written many papers recently, but I did write a lot in grad school. All right, where alpha, beta, and gamma are constraints that can be determined by a small grid search. Intuitively, phi, I'm pretty sure that's phi. Phi is a user-specified coefficient that controls how many more resources are available for model scaling. So if you're working with really limited compute, you'd make phi smaller. If you have a lot of budget to blow, you might make phi bigger and see how much larger your model can get. Making sure that the increase in model size also is leading to the most efficient increase in accuracy, or whatever metric it is that you're using. Well, alpha, beta, gamma specify how to assign these extra resources to network width, depth, and resolution, respectively. Notably, the flops of a regular convolutional operation is proportional to depth, width squared, resolution squared, i.e. doubling network depth will double flops, but doubling network width or resolution will increase flops by 4 times. Okay, so this proportion is to ensure that we are optimizing for the lowest number of flops we can have. Since convolution operations usually dominate the computation cost in convnets, scaling a convnet with equation 3 will approximately increase total flops by the dot product of alpha, beta squared, gamma squared to the 5th power. In this paper, we contrast alpha, beta squared, gamma squared approximately 2 or proportional to 2, such that for any new phi, the total flops will approximately increase by 2 to the phi. So this phi parameter here is one that you would set based on the number of resources that you have available, and as you increase phi, you will get roughly, and there is a footnote here, they might differ due to rounding, will increase by roughly 2 to that power. So if I add 1 to phi, I will double the training time and the inference time of my model. Maybe not inference time, training time. All right, EfficientNet architecture. Mismo says, is it just me, or actually the novelty of this paper is very little? I would say that it's pretty novel, actually. Most papers make incremental, improvements to the literature. This paper has 2 contributions, which is a little bit rarer. And the big contributions are, instead of manually picking how you scale your model, so manually picking what the dimensions will be, you do that using a learned parameter, technically 3 learned parameters. So that automates that part of the architecture design process for scaling. And then the second thing is this architecture that we haven't started talking about yet that is, I believe, completely novel to this paper. So it's building on previous work, of course, which is always what you want to do in science, or I guess engineering research. But it is, I would say, has quite a large contribution. All right. EfficientNet architecture. Since model scaling does not change layer operations, in baseline network, having a good baseline network is also critical. So you're making an existing network bigger, you are not designing a network from scratch. That's where the EfficientNet comes in. It will help you design a network from scratch. We will evaluate our scaling method using existing convnets, but in order to better demonstrate the effectiveness of our scaling model, we have also developed a new mobile size baseline called EfficientNet. So mobile size means that it should work well for embedded applications, and it'll fit on a phone. Presumably like a fairly nice phone and not like, I don't have mine anymore, like one of the like old style Nokia type of phones, but should require much less compute. Inspired by Tan et al. 2019, we develop our baseline network by leveraging a multi-objective neural architecture search that optimizes both accuracy and flops. So you want the model to do well, and you also don't want to do more operations than you have to. Specifically, we use the same search space as Tan et al. 2019, using ACM, so the accuracy of M, times flops M divided by T, as the optimization goal, where ACM and flops M denote the accuracy and flops of a model M. T is the target flops, and so this bit is raised to the Wth power, and W equals negative 0.07 is a hyperparameter for controlling the trade-off between accuracy and flops. Unlike Tan et al. And Kai et al. 2019, here we optimize flops rather than latency, since we are not targeting any specific hardware device. So they don't to do fewer operations rather than having specific latency on a given device. Our search produces an efficient network, which we named EfficientNet B0. Since we use the same search as Tan et al. 2019, the architecture is similar to MNASnet, except our EfficientNet B0 is slightly bigger due to the larger flops target. Our flops target is 400 million. Table 1 Table 1 shows the architecture of EfficientNet B0. Its main building block is Mobile Inverted Bottlenet NB-Conv, Sandler et al. 2018, Tan et al. 2019, to which we also add squeeze and excitation optimization. Don't know what those are. Those sound like CNN specific things. Nalim says multi-objective neural architectures. I believe it was a multi-objective architecture search, not necessarily that the final architecture has multiple objectives. So that was to find the sort of the skeleton of the model, and then when training the model, you wouldn't necessarily also target the flops target, because that's going to be dependent on the overall architecture of the model and not necessarily the setting of the parameters. That makes sense. And Frank says, what counts as novel depends heavily on what field you're working with. ML papers tend to be smaller and more incremental than mathematics or statistics papers. By ML standards, it's very novel. I'm not dissing ML research. They're doing lots of crazy research, including this. Yeah. Also in machine learning, the publication cycle also tends to be very fast. So I'd say it's fairly common to write a paper in like 3 months. I don't know how long it took to write this paper, but that's fairly standard for an ACL paper if you have a whole lab working on it. But in math, you may be working on a paper for like 10 years. The publication cycle, and my impression is that the publication cycle in math is much slower than it is in machine learning research. So, but yes, disciplinarity. All right, little step of coffee. So they used this architecture search the architecture search was multi-objective to find a baseline model, and then they are going to be doing some compound scaling using the method defined here. So step 1, we first fix phi, pretty sure that's phi. No one's corrected me, so I'm just going to go with phi equals 1, assuming twice more resources available, because remember that for every increase in phi, every unit increase in phi, you double, you increase the flops by 2 to the phi. That's not doubling. That's exponential. A little coffee. And do a small grid search of alpha, beta, gamma based on equation 2 and 3. above. In particular, we find the best values for EfficientNet B0 are alpha is 1.2, beta is 1.1, gamma is 1.15, under our constraint of alpha, the dot product of alpha b squared and gamma squared is proportional to 2, or approximately 2. I don't think that's actually proportional. I think that's approximately. So they did a grid search and they found these scaling factors. So for this particular model, you would want to increase depth, then, I mean, you're going to increase them all together, but depth will increase the most, then resolution, and finally width. Yeah, Swan says, it's a boring paper. Oh, I think it's a pretty interesting paper. And Frank says, oh, not 10 years long, but yeah, it's long. I have a pretty small sample of mathematicians, but yeah. Linguistics can also be extremely long, especially if you're doing field work. Yeah, disciplinarity. All right, so once they find the grid search, we then fix alpha, beta, gamma as constants and scale up baseline network with different phi using equation 3 to obtain EfficientNet B1 to B7, details in table 2. Notably, it is possible to achieve even better performance by searching for alpha, beta, and gamma directly around a large model. But the search cost becomes prohibitively more expensive on larger models. If you're trying to see if making a extremely large model slightly wider is going to help, then you do have to train the model. And I think we've talked about how neural architecture search is very computationally intense in general. So I really like this approach of finding a base model and then scaling it and then being like, well, I mean, you could probably eke out like another couple percentage points by doing the scaling on the larger model, but at what cost? An extremely substantial one. That's the answer. A big cost. Our method solves this issue by only doing search once on the small baseline network, and then use the same scaling coefficients for all other models. And that gets you the benefit of you have like a nice little buffet of models depending on the amount of compute you have available. You can be like, oh, B2 is going to work for this project, or oh, B6 is going to work for this project. And ideally, you can use the same architecture for multiple problems with like some tweaks if you're using images of a different resolution or something. So I think that's pretty cool. All right, section 5, experiments. In this section, we will first evaluate our scaling method on existing conv nets and the new proposed efficient nets. So existing architectures and then the architectures that they've just proposed based on the neural architecture search, which is optimized for both accuracy and also number of operations per second. As a proof of concept, we first apply our scaling method to the widely used mobile nets, Howard et al. 2017, Sandler et al. 2018, and ResNet, He et al. 2016. Table 3 shows the ImageNet results of scaling them in different ways. Compared to other single-dimension scaling methods, our compound scaling method improves the accuracy on all these models, suggesting the effectiveness of our proposed scaling method for general existing conv nets. Table 1. Oh, so we haven't actually looked at table 1. I'm sure it was somewhere in the text and I just skipped it. Okay, so what they're doing here is this is the stage and then the operator. So this must be okay, so this is the baseline network. I was like, I don't get how this is enough information for a single network. Okay, so each row is a stage in the network, so it would be equivalent to one of these guys in the convolutional neural network. And we start out with higher resolution, lower channels, and then as the network evolves, you go through stages, you get lower resolution, more channels. Presumably there are 1280 classes in the final classification problem? I don't know. I'm not that familiar with ImageNet. And the number of layers. So the things they want us to get from this are literally just a description of the model. So the resolution goes down, the channels go up, and then this is the number of layers and the operator for performing the convolution, so the convolutional operator. Okay. That makes sense to me, and presumably we'll come back to it if it's particularly relevant. But this just seems like implementation details. I don't think, like, it's cool that they found these details, but I don't think we need to go through those in great depth. All right, so they tried scaling MobileNet and ResNet, and they done good in Table 3. So here is Table 3, and they took the baseline net, they made it wider, they increased the resolution, and then they scaled the resolution, depth, and width using their trained parameters from the convolutional scaling. And what was it called? Compound scaling method. Thank you. Sorry, the C was not convolutional, it was compound. So the compound scaling model performed better than the baseline or the model scaled by width or resolution. I don't know why they didn't include depth here. Presumably they had a reason. And then looking at, so that was MobileNet v1, MobileNet v2. Again, they scaled, I guess not again, they scaled in all 3 dimensions. Increasing that did not increase accuracy as much as scaling on 3 dimensions, so compound scaling, using, presumably the compound scaling was tuned on each of these models, so it's specific to each model what the alpha, beta, and gamma values are, because those are learned. And then ResNet, again, they got the largest improvement by scaling the model on 3 dimensions instead of just 1 at a time. And then compared to the earlier results where people were doing compound scaling, these values are not manually tuned, they are learned. So that's the benefit there. Table 2, all EfficientNet models are scaled from our baseline EfficientNet B0 using different compound coefficient phi in equation 3. ConvNets with similar top 1, top 5 accuracy are grouped together for efficiency comparison. Our scaled EfficientNet models consistently reduce parameters and flops by an order of magnitude, up to 8.4 times parameter reduction and up to 16 times flop reduction than existing ConvNets. So here you have, remember they had 7 different models of varying scales. So B7 is the biggest one, B0 is the smallest one, and they increase incrementally using this compound scaling as you go up. I don't think I can fix the fuzz. I'll deal with that later. And at every stage, an EfficientNet model is outperforming other models of a similar size. So yes, it looks like the accuracy for top 1, so the class you guessed, the class you said was the most likely is the class that the thing is. Yeah, okay, better. Is the class that it is, and top 5, you guess the correct class is one of the top 5 classes in your model output. So more accurate. Nope, actually they have just bolded theirs instead of bolding the most accurate one. So it is the most accurate here. It is not the most accurate here. Exception is presumably Francois Cholet, is more accurate in top 5 accuracy and in top 1 accuracy, but it also uses 23 million parameters as opposed to 7.8 million parameters. And like an order of magnitude more flops. So presumably Exception, even though it has slightly better performance, is much larger and harder to train. So it's about 12 times larger. And then B2, so this is, so the EfficientNet is not outperforming in terms of accuracy the other related models, but it is outperforming pretty substantially in terms of size, model size, so it's much smaller. B3, same story, much smaller, roughly as good, but not quite. B4, again, not, so it actually does have the top 5 accuracy here. But at some point, I don't know, I've been thinking about this a lot. At some point, the model that you've trained is just sort of like one sample out of all the models that you could train, especially if you're doing random initialization. And you can't guarantee that you're getting to the actual global minima. And like, if you could, congratulations, you've won machine learning. Please accept your Nobel Prize. There isn't one in machine learning. So at some point, like really small differences in accuracy, it might be due to variations from other sources, but much smaller. And the same for B5 and B7. And both of these, it looks like, so B7 for sure is an improvement on the current state of the art GPipe, and B5 is an improvement on top 5 accuracy, but not top 1 accuracy. And again, much slower. It's only 9.9 billion parameters instead of 41 billion parameters. So getting fairly good results, much smaller model, which is, that's what I'm interested in. I want to know about them little models. I'm less interested in we made it bigger and it did better. All right. Hello, everybody. Table 3. I think I read table 3. Yeah, we went through table 3. Anurag says, how about a Kaggle reading discussion on the attention mechanism? We did read the Vaswani paper, Attention is All You Need, where there was quite a discussion of attention. Although attention is sort of a general term that refers to a couple of different things. So it might be helpful to read a review paper of that at some point to sort of disambiguate those. But yes, we have done a little bit of reading on attention. Coffee. Okay. So, and then table 4, which we haven't gotten to yet, but we might as well just look at it, shows that EfficientNet has a 5.7 times speed up, the little one, as opposed to ResNet 152. And then as opposed to GPipe, it has a 6 times speed up, not 6%. So much faster at inference time, which is helpful if you are trying to do things, on a mobile in an embedded system that has to happen very quickly. All right. ImageNet results for EfficientNet. So far, we've just talked about their comparison to MobileNet and ResNet and other similar models. What about EfficientNet? Let's find out. We train our EfficientNet models on ImageNet using similar settings as Tan et al. 2019. RMS prop optimizer with decay 0.9 and momentum 0.9. Batch normalization momentum 0.99. Weight decay 0.00001. I think I did that right. Initial learning rate 0.256. The decay is by 0.97 every 2.4 epochs. Okay, I was gonna ask if they were gonna. Yeah, they hadn't talked about learning rate for some reason. I was like, oh, they just talked about learning rate and they said that it was stable. No, they did not say that. I just made that up. We also use swish activation. What the heck is swish activation? Ramachandran et al. 2018, Elfwing et al. 2018, fixed augment-to-augment policy, Kubek et al. 2019, and stochastic depth with a dropped connect ratio 0.3. Don't know what those are. Guessing those are specific to convolutional neural networks. If anyone has more information, please feel free to jump in on the chat. I don't want to go and chase these papers down. But if you are looking for further readings in convolutional neural networks, those might be a good choice. As commonly known, the bigger models need more regularization. We linearly increase dropout, Srivastava et al. 2014, ratio from 0.2 for EfficientNet B0 to 0.5 for EfficientNet B7. So more dropout as the model gets bigger. All right. Table 2, oh, we read that, shows the performance of all EfficientNet models that are scaled from the same baseline EfficientNet B0. Streeton, STNG, says swish equals inverse sigmoid. Oh, interesting. It looks like a swish. I guess swish from your point of view. How would that work? Wouldn't that like invert your activations? Anyway, thank you. I will look into that later at a different time. So the increased dropout as the models get bigger. Those are just sort of implementation details. I don't think we need to dive into those too deeply. Table 2 shows the performance. I already read that. Our EfficientNet models generally use an order of magnitude fewer parameters and flops than other convnets with similar accuracies, which is what we found going through the table. In particular, our EfficientNet B7 achieves really good accuracy with 66 million parameters and 37 billion flops, being more accurate but 8.4 times smaller than the previous best G-pipe. Figure 1 and Figure 5 illustrate the parameter accuracy and flops accuracy curves for representative convnets, where our scaled EfficientNet models achieve better accuracy with much fewer parameters and flops than other convnets. Notably, our EfficientNet models are not only small, but also computationally cheaper. Yeah, that's what I like to hear. For example, our EfficientNet B3 achieves higher accuracy than ResNet XT101, C et al. 2017, using 18 times fewer flops. Let's scroll up. So that's that figure? I think that's this figure. So these are the number of operations. This is accuracy. The sort of gray dotted lines are, I don't know what the differences between these two, but the point is that this red solid line here, which is the different ImageNet models, you have greater accuracy for fewer operations, even as you increase the number of operations, and you also see that you're sort of starting to reach that decay rate where doing more operations is not helping you as much as it was earlier on. So just looking at this sort of like, where's the elbow? It looks like B4 is about the point at which you get diminishing returns on having additional operations. So, Layla says increasing dropout doesn't increase model size. No, but you should have more dropout as your model is bigger because you need additional regularization, because it's more likely to overfit, because it can describe a more complex space, if that makes sense. So no, increasing dropout shouldn't change your model size, but you need more of it if your model is bigger. GANs versus CNNs, pretty different. Pretty different. I think GANs are mostly used for image generation at this point, and CNNs are mostly used for especially object detection, and I think also maybe like bounding stuff, maybe. And also a lot of like audio recognition, because people take the audio signal, transform it into a spectrogram, which is time, frequency, intensity, and then run the CNNs on that. So that's been very effective in the audio domain as well. Question about attention in OCR. If someone else has more pointers for our Anurag, please feel free to drop them in the chat. And Wiz here says, EfficientNet models are slow, especially in Keras. Interesting. I would not necessarily guess that they would be, because it sounds like you do need fewer operations for a model with similar accuracy. Interesting. Again, I haven't played around with them, so. All right, where were we going? To validate computational cost, we have also measured the inference latency on a real CPU as shown in Table 4. People don't look at this often enough. So inference is when you go to actually apply the model, how long does it take? And if, for example, you're trying to do, I don't know, real-time speech recognition is an example. If there's enough inference, you get like a lag, and it's frustrating as a user. So the lower your inference time, the lower the lag, which is good. Thalas says so in this one, the blue dashed line here in the middle are CNNs found via neural architecture search. So the EfficientNet architecture was also found during doing neural architecture search. So this is hand-built models, neural architecture search models, other neural architecture search models with this particular scaling thing. Complex scaling? Why can't I remember what the C is for? Compound scaling method as proposed in this paper. Thank you, helpful. Is regular UNet or UNet better than attentional neural networks? Your thought? Well, I don't know. I think it depends on what you want to do. I am less familiar with vision than I am with NLP. I only got my PhD in one of them things, and it's not the vision one. All right, so faster to train, faster to inference, comparable results, and in some cases, state-of-the-art results. Transfer learning results for EfficientNet. We have also evaluated our EfficientNet on a list of commonly used transfer learning datasets as shown in Table 6. We borrow the same training settings from Kornblith et al. 2019 and Huang et al. 2018, which take ImageNet pre-trained checkpoints and fine-tune on new datasets. So you train your big model on ImageNet, and then you finish training on a second dataset. So similar to BERT or GPT-2 or all of the other NLP transfer learning models we've talked about on the channel. Table 5 shows the transfer learning performance. 1, compared to public available models such as NASIN-Net-A, Neural Architecture Search Net-A, Zoff et al. 2018, and Inception v4, Skazgadi? Oh, I definitely didn't say that right. Our EfficientNet models achieve better accuracy with 4.x average up to 21x parameter reduction. So fewer trainable parameters, but better accuracy. Great, love that. Love to hear that. Compared to state-of-the-art models, including DAT, Deep Architecture Transformation, I don't know what it stands for, that dynamically synthesizes training data, and GPipe that is trained with specialized pipeline parallelism, our EfficientNet models still surpass their accuracy in 5 out of 8 datasets, but use 9.6 times fewer parameters. So they're comparing it to other models. DAT dynamically synthesizes training data, so it looks like they're doing sort of dataset augmentation through synthesis during training. That's wild. That sounds cool. And GPipe, and this is the model that they were talking about, that they had to develop a new parallelization architecture in order to actually fit it anywhere across multiple things. What are they called? Processing units? Processing units, I guess. Yeah. So they're saying that their model does better, and it is much smaller, and also you don't have to design a new parallelism method to actually train it, that's nice. What is a GPipe? So GPipe is the model, and there's a little bit of a lag. GPipe is the model that was very large, and I believe before this paper was published, had state-of-the-art on ImageNet. Scroll. Figure 6, and we can go back up and look at these figures, compares the accuracy parameter curves for a variety of models. In general, our EfficientNets consistently achieve better accuracy with an order of magnitude fewer parameters than in existing models, including ResNet et al. 2016, DenseNet, Huang et al. 2017, Inception, S et al. 2017, and NASNet, Zoff et al. 2018. And as Thalas pointed out, these are also found through neural architecture search. So hand-built, neural architecture search, and EfficientNet was also found through neural architecture search. And the promise of neural architecture search is that it helps us find good families of models, and then we can just use those families of models, and you don't have to keep doing the neural architecture search because, again, very expensive. All right, so have we looked at this paper yet? I don't think we have. Okay, so this is the transfer learning one. So this is training on one data set, specifically ImageNet, and then seeing how well you do with other data sets like CIFAR 10, CIFAR 100, don't know what's in them, pictures probably, BirdSnap, pictures of birds, Stanford cars, oh I do know this, you have to identify the car, like make and model, flowers, aircraft, pets, and food. So this is comparing different models. So, okay, so this is the best publicly available result at the time that the paper was published. Let me zoom in. So this is the current state of the art. So the EfficientNet B0 set new state of the art for CIFAR 10, CIFAR 100, BirdSnap, Stanford cars. I'm just checking if these numbers are even parity with state of the art for flowers, not for aircraft, not for pets, and yes for food. But the really interesting thing here is that it was achieving really good results with using far fewer parameters, because the fewer trainable parameters, less things you have to train, the quicker you can do backprop, all that sort of thing. So it just speeds up the whole thing. And it makes the model a little smaller, it's easier to serve, it's easier to store, smaller, gooder, more efficient, hence the title, EfficientNet. And it looks like here, so for CIFAR 10, B0, which is the smallest model, got a achieved state-of-the-art with 21 times fewer parameters. So that's fantastic. Sounds like a real improvement. And then these are best reported results. So these are from other papers, and these are, I believe, comparing to maybe leaderboards where they're all validated very consistently. So sort of like a Kaggle competition would be my guess what that is. And here it looks like EfficientNet is sometimes setting state-of-the-art. Sometimes it's these other very large models, the GPipe and the DAT, that does synthetic image production during training, which again, that's wild. That's really interesting. And has far fewer parameters than GPipe. It looks like the number of parameters for DAT is not set. Let's see if they talk about that in the... DAT donates domain adaptive transfer learning, Nguyen et al. 2018. Here we only compare ImageNet-based transfer learning results. Transfer accuracy and number of parameters for NASNet, Inception v4, ResNet, and all of those are from Kornbluth et al. 2019. GPipe trains giant models with specialized pipeline parallelism library. Okay, so domain adaptive transfer learning. So, okay, so this is not actually a specific model? Ooh. I'm not super familiar with this. Let me put it this way. I've never heard of this before. I've never heard of DAT before. That doesn't mean it's not good. It's just I'm not familiar with it. All right, and then figure 6, model parameters versus transfer learning accuracy. All models are pre-trained on ImageNet and fine-tuned on new data sets. So here we have accuracy, here we have the number of parameters. So bigger models are bigger, I don't know what, so bigger models would be further to this side, smaller models further to this side, and each of these symbols is a specific type of model. So GPipe is this little one that's showing up here in the corner most of the time. And then these connected ones are the various EfficientNets, and you can see that yes, as you increase the number of parameters, you do get higher accuracy, but even if you don't have that many parameters, mostly these models are still achieving higher accuracy. And you can also see the general trend: more parameters in general, more accuracy. Or higher accuracy, not more accuracy. It's a weird way to put it. So it's particularly for CFAR 10, CFAR 100, Stanford CARS, Food 101. It looks like for those data sets in particular, EfficientNet models are much, much better. Yeah, interesting. And also, do you know that this is on a log scale, so these are not linear improvements. I don't know how well you can see the scale there. All right, so transfers, good. Which is nice, because it means that it's not a model architecture that only works on specifically ImageNet and is super overfit to that data set, because that is one of the worries, I think, especially in the computer vision literature, is overfitting to particular data sets. All right, discussion. To disentangle the contribution of our proposed scaling method from the EfficientNet architecture, because remember there's two contributions of this paper, Figure 8 compares the ImageNet performance of different scaling methods for the same EfficientNet B0 baseline network. In general, all scaling methods improve accuracy with the cost of more flops, but our compound scaling method can further improve accuracy by up to 2.4% than other single-dimension scaling methods, suggesting the importance of our proposed compound scaling. So what they're saying here is, hey, we did two things. How do we know that it's not just EfficientNet is really good and that our scaling is not actually that helpful? So they took ImageNet and then tried scaling it by each of the parameters individually, and making the model bigger did help overall, but using their compound scaling method had a much higher rate of improvement than scaling one dimension at a time. I guess resolution is 2 dimensions. In order to further understand why our compound scaling method is better than others, Figure 7 compares the class activation map for a few representative models with different scaling methods. All these models are scaled from the same EfficientNet B0 baseline, with about 4 times more flops than the baseline. Images are randomly picked from ImageNet validation set. As shown in the figure, the model with compound scaling tends to focus more on relevant regions. Nope. None of that. Shoot. Tends to focus more on, tends to focus more on relevant regions with more object details, while other models are either lack of image details or unable to capture all objects in the image. Okay, so here we have a picture of some macarons, so it's a type of cookie, and here we have a picture of a maze, and they did say these were randomly picked, so we know they weren't cherry picked to get the best possible example for the paper. And the baseline model has attention sort of in the middle of the image here, sort of around the side of the image. Making the model deeper sort of lowers the attention area. It's not really attention. Focus region, shall we say. Making the model deeper here does help. Making the model wider, it looks like does not help as much, actually. It sort of looks like it just sort of centers the decision region to sort of the middle of the image. I don't know. Higher resolution, again, does, like, it helps a little bit. Obviously, like, again, it continues to go up, so it is improving accuracy, but it's not sort of to the same level as the compound scaling. Although I would say of the 3 types of scaling, it looks like the higher resolution better matches with sort of my intuition about what you should pay attention to as a human. And then the compound scaling is really looking at each of the macarons, and it's particularly focusing on the filling of this one. And the compound scaling for this one is really looking at the maze and ignoring the white space around it. So that's sort of helps to bolster the intuition that if you're scaling all of the 3 things, even if you still have the same number of operations, you can achieve more intuitive representations, I guess, with compound scaling. Conclusion. Oh, is that it? Oh, we're to the conclusion now. In this paper, we systematically show ConvNet scaling and identify that carefully balancing network width, depth, and resolution is an important but missing piece, preventing us from better accuracy and efficiency. To address this issue, we propose a simple and highly effective compound scaling method, which enables us to easily scale up a baseline ConvNet to any target resource constraints. So remember that fee constraint is one that you pick, and you would pick that based on how much time, money, data you have. Of course, you can't also just like make pictures greater resolution, so you might also be constrained by the resolution of your pictures. Powered by this compound scaling method, we demonstrate that a mobile-size EfficientNet model can be scaled up very effectively, surpassing state-of-the-art accuracy with an order of magnitude fewer parameters and flops on both ImageNet and 5 commonly used transfer learning datasets. And then the acknowledgments, and I'm not going to try and read all of these names because I will get them wrong, but also acknowledging these other individuals. So that's the paper. Overall, I think it's very interesting. It sort of makes me want to train a computer vision model. We'll see. I don't really have any projects that would be a great fit for that in the medium near future. I find it pretty, I find the compound scaling to be pretty intuitive. And I also really like that the scaling parameters are learned. I think there's a lack of principled design principles for neural network architectures. There's a couple. For example, if your hidden layer isn't wider than your input layer and your output layer, you can't describe a non-contiguous decision region. And that has a formal proof, but there's very few sort of formal guidelines for designing neural network architectures. And this does not, so efficient network is an architecture you can use. It is not a design principle that you can use to design new architectures. And I think the idea of neural architecture search is that, hey, it's really hard for us to figure out what those architectures are going to be just because the search space is so large. So does this teach you what architecture to use? It teaches you that one exists and you could use that one. But it does produce a principled way for learning the ideal scaling, not idealing, for learning a set of good scaling parameters, and shows that scaling your network along 3 dimensions rather than one at a time can work very well, even with learned parameters, as opposed to these other papers which used hand-tuned parameters. And I think that is very useful. And I don't know if someone has applied a similar compound scaling method to NLP. It's definitely possible. It's something I haven't run across before, but I wouldn't be surprised if this had inspired related work. I'm thinking about specifically the transformers have sort of a similar architecture where you have multiple layers stacked on top of each other. So you could do something similar where you expand the attention span, you increase the depth of the layers. Yeah, they're not changing the number of layers here. And you also increase the width of the network, and you could scale your transformers on 3 parameters that way. Hyperparameters that way. I don't know how well that would work. It might work very well. I don't know. If someone hasn't done it, there's a research idea for y'all. From the chat, Anurag says, it would be great if we could start some practical deep reinforcement learning. OpenAI is just doing great things in this domain, but I don't know how to start creating stuff like that. Yeah, definitely reinforcement learning is something that we are thinking about. Yeah, noted. Thank you. Good feedback. Can you suggest books for NLP? I always suggest, I don't have my copy near me, Speech and Language Processing by Drafsky and Martin. It's available for free online. If you're looking for a more sort of just like, hey, I want to do the thing, the Tidy textbook in R is also very good. That's by Julia Silge and Dan Robinson. And that's also just, it's a very practical, like, hey, you need to analyze some text, here's how you do it. Introduction, a little bit like less theoretical NLP research. So I also recommend that one. All right, it is 10 o'clock for me. I'm going to wrap this up because I have so much to do today. I will not be live on Friday. I'm going to be out of town for a family thing. I may have a video up. I don't necessarily want to promise it. We'll see if I get time to film it today. But regardless, I will see you next Wednesday for a new paper, which I haven't decided what it will be yet. I'll probably do some sort of poll, and look out for that on the YouTube channel, the community tab, and then also probably on Twitter. It'll be up on there. Thank you so much for joining me today, guys. I hope you found this helpful. I'm definitely glad that we finally read EfficientNet because it's been in the wings for like 6 months at this point. And it was worth the wait. I would say a very enjoyable paper to read, and I learned a lot. And I will see you all on Kaggle.